Good morning. It's Christmas break. I woke up today and I want to make a video about the Laplace transform. They never explain it. They just kind of throw it at you, and the formula is absolutely crazy. And there's very little justification given for why we're doing it or where it comes from or anything like that. And I think that I have just like a really simple way of looking at it. If you put your mind in the right place, it's actually like a really natural thing to do. Pierre-Simon Laplace was a French mathematician who was alive in the 1700s and early 1800s. And he was a polymath, which is just kind of like a fancy way of saying Renaissance man. And he made a contribution to a lot of different things, celestial mechanics, classical mechanics, probability, this thing called Laplace's equation. It's really beautiful. The Laplacian differential operator, love this. And then also the Laplace transform, which we're going to talk about here. His Wikipedia page, he's got a lot of things to say about. Oh, here's a little bit of a kind of a thirst trap one there, so you can enjoy that. Didn't know that was going to be part of the video. Yeah, so let's talk about the Laplace transform. Let's start by looking at one of my favorite math objects, the dot product. You may have seen this before, so I'll try to be brief. The way it works is it's a way of combining two vectors. Sometimes people call it the scalar product. What you do is if you have two vectors, you multiply each of the coordinates. So the first coordinate of the first vector times the first coordinate of the second vector. You do that a bunch of times and then you add them all up. And I have a simple example here, and you can see that like I do the 2 times the 4 and the -1 times the 6. And then you just add up all those things and it gives you the answer. So this is the way that we calculate this mathematical operation called the dot product. One easy way to understand what the dot product is doing is to take a vector and calculate its dot product with some very basic vectors. So I've chosen here what I think to be some basic vectors. We also call these vectors a basis. So let's just do it. What do you get if you calculate the dot product of I and V? Well, this part right here, the second coordinate and the third coordinate are just going to turn into 0 when you multiply them. So, and then when you do 1 times that first coordinate, you're just going to be left with the first coordinate. So when you calculate the dot product of V with I, you're just going to get the first coordinate. When you calculate the dot product with V with J, you're just going to get the second coordinate. Can you see what I'm doing there? And then likewise, maybe I'm over explaining this. When you do the dot product of V with K, you're going to get the third coordinate there. So the dot product can take a vector and sort of tell you how much of that vector comes from the first coordinate, how much of that vector comes from the second coordinate, and how much of that vector comes from the third coordinate. Answering questions like that, how much of this does that, we call those things projections. Once you have a vector decomposed into each of these little pieces, it's actually really easy to recompose it and recover the vector back. Here I have just written the meaning of, like this is how we write it in physics class. So this is the output of this like process of decomposing it. You're saying how much of my original vector is in the I direction? Well, 2 is the amount that it's in the I direction. So if you just like do the vector arithmetic with this expression, what are you going to do? So you're going to take this like 2 times -1, because I'm like just rescaling all of these coordinates. But look, those zeros, nothing's going to happen in that. And then in all of the other pieces of this expression, there's always a 0 in that first coordinate there. So, I think it's obvious to see if you just look at this, what are you going to get if you just add these things back up? The only possible part of this that could contribute to the first coordinate is this piece right here, and you're going to get a 2. Then for the middle coordinate, you're going to get a -1, and for the last coordinate, you're going to get a 3. All right, so there's the process. I know this is like really simple, but the takeaway of this is you can always take a vector, decompose it into its basic parts, and once you've done that, it is very easy to then recompose it back into what the vector was originally. Okay, so I just summed up what that little conversation was about. So here's the conclusion. You can always take a vector, okay, and then you can use the dot product to decompose that vector into a bunch of components, just like a list of numbers. And then you can use this sum of the products logic in order to take all of your components and then turn that back into a vector. All right, I came back outside because I'm hoping that the change of scenery is gonna grab your attention. What I'm gonna do now is I'm just gonna do all of this all over again, except I am going to replace the word vector with the word function, okay? And I swear that there is a lot of mathematical depth to this idea. So, now you're armed with this new kind of knowledge. This is an awesome trick. Pretend that your functions were really vectors. We are going to do this really cool, mathematically mature idea of taking the word vector and replacing it with the word function. And we're going to apply this concept to this process of taking an object, decomposing it as components, and then recomposing it back as the original object. But we immediately get stuck. It was obvious, when we were doing vectors, what we should choose as our kind of basic vectors. This is really clear what our basic vectors are. But now that we're going to do this again with functions, it's not so obvious. What should we choose as our kind of basic functions? The thing is that there isn't really one choice. In fact, there isn't really one choice when we choose what our basic vectors look like as well. There's other totally valid choices, but we have a goal in mind. The goal that we're trying to achieve is to be able to solve differential equations. We want to somehow decompose our vector as components and then do some kind of math over here with just the components and then be able to recover back what the answer was. So whatever we choose as our sort of basic functions, we want these functions to kind of play nice with calculus. We want to be able to take derivatives easy, and we want to be able to do integrals easy. So let's just think for a second. What function out there is it really easy to calculate derivatives of? Okay, so obviously exponential functions are a good candidate here. So what I'm trying to do is think of some kind of basic functions. I want them to be very simple functions, and I want to be able to do calculus with them easily. So here I've done it. I've just picked some kind of really basic functions. I here could be e to the t. J, this is the second coordinate, could be e to the 2t, and k could be e to the 3t. And there I've done it. I've come up with a bunch of very basic functions that we could use to decompose our original function. But there's a little bit of a problem. And the issue is when you start adding things up, it's actually possible for the answer to come out diverge. When you start calculating these dot products, you could get infinity. And the functions that I have chosen here are kind of a bad choice, right? Because, exponential functions grow very, very quickly. So there's a lot of area under here. This growth rate is really high. So I don't necessarily want to use e to the t, because then if I start adding things up, the area could blow up very quickly and I could get diverge. So what I want to do is I really want to have these areas under these curves be finite a lot of the time. So what I'm going to do is put negatives under there, and that way we get exponential decay curves like this that are going to have very small area underneath them. So that's it. We've come up with our class of very basic functions, kind of the function version of I and j and k. So how do we calculate the dot product of two functions? Well, you know what? Let's just take whatever the definition of the dot product of two vectors was, just Control-C, Control-V, just copy and paste that into the definition of dot products for functions. So, all right, so let's interpret the dot product for vectors. What you do is you multiply each of the coordinates and then you add them all up. And I can actually interpret that as the area underneath a bar graph. Here, V1U1, since this distance across the bottom there is 1, V1U1 is the area of this rectangle. So you multiply all of the coordinates together and that gives you a bar graph. And then when you add them all up, you're going to get the total area that is under the graph that you get when you multiply the two coordinates together. So, all right, so if I jump over here to the land of functions now, Now in vectors, there was only 3 possible coordinates, but now that you have functions, there's like a bunch of different possible values for t. So let me chop this up into a bunch of little pieces and add up all of the areas of those little pieces. And I think a lot of people are starting to see where this is going now. So I'm gonna calculate a sum. I'm gonna add up a bunch of things. And what are the things that I'm adding up? Well, I'm going to add up all of these areas. So the height of that area, I'm just looking at this first one right here. The height of this area is going to be f of t1 times e to the negative t1. And then the width across the bottom there is going to be delta t. All right, and then I think everybody sees where I'm going with this. The next thing that I'm going to do is choose smaller and smaller values for t. So I'm going to take the limit as delta t, sorry, smaller and smaller values for delta t. So I'm going to take the limit as t goes to 0, and you're going to get the integral of f of t e to the negative t dt. And this integral is going to run over whatever the domain was. So in our original context, the domain was just 1 and 2 and 3. And for a lot of differential equations problems, the context is you're looking what can happen from like time starting now all the way into the future. So this doesn't have to be the integral from 0 to infinity. We're just doing this in the context of a lot of like popular differential equations problems. So that's it. This expression right here is how you calculate the dot product of two functions. And what I've done here is just done this dot product with our most basic kind of function. So I think it's all coming together here. Let me just wrap this up and make the final conclusion. The Laplace transform is a generalization of the idea of decomposing a vector into components. When you calculate the dot product of a vector with a very basic vector, that tells you a coordinate in that direction, or a first coordinate. Exactly the same way, you just cross out the word vector and you write the word function, and this is a way of decomposing a function into a bunch of coordinates. Of course, in R3, if you have the vectors and they're 3D vectors, they're of length 3, then there's only 3 ways to do this. But f of t has a bunch of different coordinates. For each value of t, you get a different coordinate of the vector. So you can have a first coordinate, or a second coordinate, or a third coordinate, or a fourth coordinate, and it just goes on and on and on and on and on. In fact, one thing that's really interesting about this is it doesn't just have to be whole number coordinates now, right? In fact, here I can squeeze in a 1/2 coordinate in between, and I could just do, right? I could just do f of t dot product with e to the negative 1/2 t, and that will kind of tell me the 1/2 version of these coordinates. So that's going to leave you with kind of an interesting idea to think about. In 3-dimensional space, I had vectors of length 3, and here not only do I have a list where for each whole number I get a different coordinate of that vector, but in fact for every real number I get a different coordinate of this vector. So the Laplace transform, it has a really scary formula, but if you plug in a value for s, all it's really doing is the same thing as like plugging in this value for n. It's just telling you what the coordinate of that function is in that place. So hopefully you can walk away from this feeling a little bit better about what the Laplace transform is. And I love talking about these things. So, if you ever have a question or you want to chat about it, please just let me know, and we could just go on about the Laplace transform all afternoon.